So we want to be able to find zeros of polynomial functions, and one way to do that is with factoring. And remember, when you factor, the important thing to remember or to think about is that you shouldn't factor until you have the equation set equal to 0. So whenever you're doing quadratics or polynomials or anything and you're trying to factor, the first step is always get everything on one side equal to 0 on the other side. If it's in factored form, if it's not factored, then factor it if you can. And then what we do is set each factor equal to 0. So if we look at this first example, 3x times x minus 6 squared times x minus 16 squared, I can see that I have three factors here. I have the 3x, I have the x minus 6, and I have the x minus 16. Now the square part isn't going to change what happens when you set it equal to 0, because the only number you can square and get 0 is still just 0. So I take each of those factors, I set them equal to 0, and I solve. So divide both sides by 3, I get x equals 0. Add 6 to both sides, I get x equals 6. Add 16 to both sides, and I get x equals 16. So there are three zeros, and they are 0, 6, and 16. So that example was nice because it was already in factored form. What do I do if my polynomial that I have is not yet factored? Well, start by factoring. 0 equals, I notice that I can take an x out of both of these terms. I'm actually going to take out a negative x because I don't like my leading term to be negative. So that leaves me with x squared minus 4. This second term that's left here is a difference of two squares. So I can factor it into x minus 2 and x plus 2. And now it looks like the first example. Negative x can be 0, x minus 2 can be 0, or x plus 2 can be 0. Divide by negative 1, x is 0. Add 2, x is 2. Subtract 2, x is negative 2. So again, I got three zeros, 0, 2, and negative 2. So in this last example, when I look here, it's not factored at all, and it doesn't look like there's anything in common. I don't really know how to factor this. So what I'm going to do in this one is I'm going to put it in my calculator. So I'm going to take this equation, x cubed plus 11x squared plus 35x plus 32, and I'm going to put it in Desmos. So x cubed plus 11x squared plus 35x plus 32. And zeros are really just x-intercepts. So what I see in this is that there are three x-intercepts, and these are approximations. So this one wasn't factorable. I couldn't have done a factoring of this one. So I see three approximations of the zeros, negative 6.164, negative 3.227, and negative 1.609. So I'm going to put that in my let me try again. So I had three zeros there. They were like at negative 6.2, negative 3.2, and negative 1.6. So not factorable. Just use the graph. Okay, so if you think about what happened up here, in this example, these zeros had like powers on them, right? And in the second example, we didn't have any with powers on them. So what we do is we talk about how that's going to make it behave. And we call that the multiplicity. So it says if a polynomial contains a factor of the form x minus h to the p, so in our first example, we had x minus 6 squared, so my p would have been 2 and my h would have been 6. The behavior near the x-intercept is determined by the power. We say that x equals h is a zero of multiplicity p. So 6 had multiplicity 2 because 6 was my 0 and its power was 2. The graph of a polynomial function will touch the x-axis at zeros with even multiplicities. I even add that it sort of bounces. It touches and turns around, kind of like that. It looks like the vertex of an x squared. And it will cross the x-axis at odd multiplicities. So evens do that bouncing thing, and odds do this crossing thing where it slides through kind of like a line. So this says, here's our function. Find the zeros and the multiplicities. I can see that there are three factors. I have x plus 5, I have x plus 7, and I have x minus 4. So subtract 5 from both sides, x is negative 5. Subtract 7 from both sides, x is negative 7. Add 4 to both sides, x is 4. In the first one, I have a exponent of 2, so this has multiplicity 2. In the second one, there's no exponent up there, so that's a 1, so multiplicity 1. And in the third one, I have an exponent of 2 again, so multiplicity 2. So at x equals 4, it's going to kind of look like an x squared, like that or like that, at x equals 4. At x equals negative 7, it's going to cross right through. X equals negative 5, it's going to do that bouncing thing again. Given the graph below, find the zeros and the multiplicities. Okay, zeros are x-intercepts, so I see it crosses the x-axis in 3, crosses or touches the x-axis in 3 places. So x equals negative 3, x equals 2, and x equals 5. At negative 3, it crosses. At 2, it bounces or touches and turns around. And at 5, it crosses. Okay, so remember from up here, when it crosses, it has an odd multiplicity. So I'm going to say that these two are multiplicity 1, the lowest odd number we can think of. When it bounces, it has an even multiplicity. So this one at x equals 2 is going to have an even multiplicity, and I'm just going to pick the lowest one, multiplicity 2. So if I'm thinking about what the equation looks like, if x equals negative 3 is a 0, then x plus 3 is a root. It's going to have an exponent of 1. If x equals 2 is a 0, then x minus 2 is a root. It's going to have an exponent of 2. And if x equals 5 is a 0, then x minus 5 is a root, again with a 1. There might be some coefficient here in the front that we could figure out later.